Well, thank you very much for inviting me again for the year to give a talk on this line of work. And I promise you, for those of you who were at here, the last workshop or the one before, it's going to be a totally different talk, so I hope it's not going to bore you. So this work comes from perhaps more directly complexity theory than many of the talks you have heard today. And I'd like to show you that there are some very nifty connections with very classical mathematics that we can use to prove classification theorems in complexity theory. That's what this is. And I would only talk about a few aspects of the connections, and I hope I can interest many of your experts here on representation theories and tensor and transformations. I think there's a lot to be done, and I would really love to hear new ideas that you can use. So the framework that I like to talk. Okay, so let me first say which Siegel theorem. Siegel has many theorems. So the theorem that I would be using, more in spirit really, because we want a very effective version of it, is to say that if you have an algebraic curve of genus at least one, then with integer coefficients, then there are only finitely many integer solutions. Okay? And in fact, there's a bigger cousin, a bigger hammer of it about rational solutions. We don't need this, actually. But even for integer solutions, even for very simple equations, many of you probably know that the behavior could be very wild. I mean, you know, if you just try a few numbers, it doesn't work, it doesn't mean that there are no solutions. And in fact, you know, the smallest solution of this is like that, okay? And if you try a little more, you find no more, then you don't think there are no more. In fact, there are infinitely many solutions, okay? They are, you know, there. Okay, so questions of this sort tend to be rather difficult, I think, in general. And it's very deep mathematical questions. But it turns out, and to my delight, that these actually are really the key to some of the proofs that we have to make in complexity theory. In this particular case, to show that certain polynomial time reductions in fact work. Okay, so the proof of hardness hinges on the fact that there are no more integer solutions. Okay, now what is edge coloring? I have three phrases in my title. One is Siegel theorem. This is edge coloring. Well, this is a definition by picture. Everybody can see what that means, right? You color the edges of a graph with various different colors, subject to certain constraints at every vertex. So at every vertex, you want, in this particular case, that they're all of this different color. That's proper edge coloring. Okay, you don't have two green edges attached to the same vertex. That's edge coloring. So what's known about edge coloring? A proper edge coloring using the maximum degree plus one colors is always possible. You know, the maximum degree, of course, is obviously a lower bound. You must use at least this many. Some graphs can be colored with this many colors, and some can't. And the universal upper bound that always works is plus one. Tate in 1880 proved that for bridgeless three regular planar graphs, this statement that a three-edge coloring always exists, which is true, is equivalent to the four-color theorem. It was a theorem at the time because it was a conjecture before, and it was proved by Kempe. And for a period of about 10 years, it was a theorem until it was found that there was an error. And that became a five-color theorem. But the statement, the Tate theorem, that they are equivalent is still valid. And this became, of course, another theorem afterwards, in the 1970s. Bridgeless is important because if you have a bridge, then three coloring doesn't exist. That's easy to prove. So therefore, in particular, for this NP question, if you will, give me a planar graph, is it edge three colorable, has a trivial NP certificate just to check for bridge. But to prove that it's correct, this certificate is correct, is essentially the four-color theorem. Okay, so there are, you know, some certificates of NP correctness is not obvious to prove that it's actually correct certificate. In general, for non-planar, this was shown in the 80s that this was NP complete. So we're talking about whether or not there exists a coloring. Okay? The corresponding problem for every NP problem, basically you can talk about a counting version of it. So if there exists one, or how many are there? Yes? Of course, if you know how many, then you can know if there exists, but in general, not the other way around. So this other class called Sharpie, which sort of talk about all the counting versions of NP, can be applied here for edge coloring, and this problem is open for all these some, I don't know, 30 some years. And most of the NP complete reductions are what's called parsimonious, in the sense that the reductions going from, say, satisfiability to a NP complete problem preserves the number of solutions. So if you knew the solution of the target problem, you could turn around and solve the counting problem of the original problem. And this way will give you a Sharpie reduction. But in this case, Dominic Welsh actually showed that this reduction for edge coloring cannot be made parsimonious. So that's perhaps why this problem is still open for counting. Okay? So the problem we are going to be talking about, the edge coloring, is the counting complexity of edge coloring. So it seems to have nothing to do with Siegel theorem, right? I mean, what does Siegel theorem have to do with this? Okay, so let me be formal about what the problem we're talking about. You're given a graph input, and you want to know the number of valid edge coloring using kappa colors. Clear? Okay? So if there are none, then it's not even kappa colorable, but in general, you want to know how many. And that's the computational problem. And for computational complexity, the problem is formulated this way. The input is measured in the size of the graph, and then output is this quantity, and then you want to know what's the computational complexity of doing this computation. Okay, is it exponential time? Is it NP complete? Is it Sharpie complete? Is it polynomial time computable? Okay, so is it clear what the setting is? So the theorem that we will be talking about is that for every parameter kappa, number of colors r, regularity of the graph, that the problem is Sharpie complete. So this was the open problem from 1980.
Sorry, so is it known to be in Sharpie?
Yeah, because you know, an NP type Turing machine can just guess a particular assignment of the edge colors among one of the k colors on every edge and verify at every vertex it is, and the number of accepting paths is exactly the number of valid edge color. So these are obviously Sharpie problems.
Just because the way you phrased the theorem, that's the only reason I asked.
Yeah, it is. It is.
Yeah, okay.
So the proof is actually separated into two parts where the kappa, the parameter equal to r or bigger, and these are proved in the framework of complexity dichotomy theorems. And that's my third phrase in the title. So I'm going now move into this description of these framework of dichotomy theorems and counting problems. These problems come in at least in three varieties of graph homomorphism, constraint satisfaction problems, and Holant problems. Okay? In each framework, there has been remarkable progress in the classification program of the complexity. So the typical problem there is almost like a meta problem where you want to say for every type of constraints that describes the problem is either going to be in polynomial time solvable or hard for the respective complexity class, such as NP or Sharpie. And so, for example, for the edge coloring, you will be talking about this local constraint function, which says that I'm sitting at the vertex, I'm looking at the edges coming in, and my decision is they must be all distinct. Okay, so that's the edge coloring constraint function. And then you say that if there isn't a local, is there an assignment to every edge so that everywhere the constraint is satisfied, then this is a satisfaction. It's a satisfaction problem, right? Okay, good. So there has been remarkable progress, I think, in all three constraint frameworks. But this particular problem of edge coloring is naturally phrased in the Holant framework. So I will turn to this first. And I want to keep the terminologies to the minimum, and I want to explain by examples. But some minimal amount of terminology is necessary. So So bear with me. We have a graph, okay, G. And then you have a set of constraint functions, like, for example, all distinct. Every local assignment must be of assigning a different edge color. And then this pi assigns a function to every vertex. So this is a labeling of constraints at every vertex. And then you look at, say, over the Boolean domain for now. You want to assign every edge to be either in or out. And then for the particular assignment of the edges of 0, 1, you look at every vertex where there's an associated constraint function, and you evaluate this constraint function locally with respect to the particular assignment on the edges that are incident to this vertex. And then you multiply them and you sum them. It's a sum of product type computation. Okay. It has a lot of rich history of trying to express things of this sort, like in statistical physics, where you have partition functions. You sum over spins of particles, and you multiply at every edge of the interaction force. In statistics, usually this product is expressed as e to the sum lambda of the sum of the local things. And these are called Hamiltonian on the exponent, and you sum of the e to the sum, okay, which is really sum of products, okay? I'm going to try to think of a constraint function as simply a truth table of length 2 to the n. So think of this as a vector or a tensor. But thinking in terms of tensor, there's a way to express it as sort of a tensor products and sums. And particularly, I think, will be interesting to the people in this workshop. You have this expression for example, the function where you have 2 to the n entries, where this thing will, when you expand out, it becomes 1, 0, 0, 0, 0, 0, 0 of 2 to the n long, plus the 0, 0, 0, 0, 0, 0, 0, 1 of 2 to the n long. And when you add them up, it has only 2 ones, 2 non-zeros at the very beginning and very end. And they are indexed by the index of 0, 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, 1, 1, and everywhere else is 0. So if you are just a computer scientist, you know this is a truth table, and it represents a particularly simple function. The function is the equality function. The all n bits must be equal. Okay, so thinking this in totality as an amalgamation of two things together as a single entity, it's just a truth table of a particular function. But you split it into this form, then you can start to talk about what's called holographic transformations. So you act this Adama matrix to the tensor nth power to this thing. Well, one of the beautiful things about matrix product with respect to tensor product is that you can distribute. Right? So you distribute the h term, and then it becomes h times this to the nth tensor power. Right? Does it make sense? So I have h times 1, 0, which is just the first column, right? And then if I do this to the nth power, this just becomes all 1 things. And if you did this of 0, 1, then this becomes 1 minus 1 to the n. And this becomes 1 minus 1, 1 minus 1. Okay? Depends on how you label the things. If you label this in lexicographically, it would be 1 minus 1 minus 1 plus 1, and so on and so forth. Okay, so basically, what you have now is two vectors expressed this way, and then now you reassemble them, and there will be cancellations happening. And this turns out, if you look at it, it's the parity function. So what we have just done is some sort of a magical transformation by the Adama matrix, this 1, 1, 1 minus 1. Technically, you could multiply by 1 over square root of 2 to be orthogonal. That will transform the equality function to parity function. Okay? And so if you think in terms of this way, then there's a natural group action. You can think of some sort of group of which H might be a member, and you would act on the set of functions, constraint functions, and then it will produce a transformation from one function to another, and they form some sort of orbits, and you can try to understand the properties of these orbits. And this is sort of in one way of thinking what holographic transformation is about. Okay, you split up the actual unitary thing, which is just a 0, 1 things, and you split arbitrarily in an algebraic way, and then you try to transform separately and recombine, and cancellation happen, and somehow you can sort of change the character of one function to another. And since this workshop is, with so many great experts in representation theory, let me just mention one simple slide of a tip of iceberg of what I think is a lot of ways that you can use your theory in this domain. This particular thing has no bearing on particular result I'm about to say, but it should suggest ways that you can apply. Right. If you take the SL2, it's the complexification of the SU2. Okay? And then since the SU2 is the Lie group, the real Lie group of SU2, the simply connected compact, there's a one-to-one correspondence between the representations of this and the representation of these without the H and the representation of SU2. And in fact, this is how you start your theory of a semi-simple Lie algebra representation. This SL2 thing is really sort of the most basic structure you try to find in every simple Lie algebra. And you have this little H and X and Y and so on. You act them, and you're trying to find that there are highest weight vectors and trying to classify them. Right? But what I'm trying to say to you now is that if you take about a symmetric constraint function, so this is just a shorthand notation to say that it's a function of 2 to the n long, but it is symmetric. It says that if the Hamming weight of the input of 0, 0, 0, 0 is Hamming weight 0, then the value is f sub 0. If the Hamming weight is 1, 1, 0, 0, 0, or 0, 1, 0, 0, whatever input coming in is a Hamming weight 1 thing, then you have a value f1. These are called the symmetric signatures or symmetric constraint functions. And you can act by an element of SU2 to transform this. And this is like basically what I did for the Adama transformation on the identity function. And this is a group action, obviously. Okay. Now, you can also do something else. You can take a bivariate polynomial, okay, homogeneous of degree n, where n plus one term, and then you act on this polynomial in this following way, where you define, starting from a p, to get a new polynomial q, where the definition of qxy is just a p of xy times u. So you think of xy as a row vector multiplied by the 2 by 2u. It gives you a new two-term thing, each of which is a linear form in x and y. And then you re-express them as a homogeneous polynomial, which have these coefficients. So you change these coefficients to those coefficients. This is, in fact, the canonical way you get the unique irreducible representation of SL2 in dimension n plus 1. And a simple theorem, you can just check yourself that they are exactly the same. So this really should suggest there are some deeper connections of signature and holographic transformations and your representation theory. In particular, we have very little understanding when the domain size, which is where the variable takes value, so either true or false, for example, that's the Boolean domain case. When that size of the domain size is more than 2, when it is not Boolean. So for example, edge coloring. I want to color red and green and blue. And on these 3 different input possible values per each variable, and the constraint function may say something. Okay? And so these are the places where I think a deeper understanding of the constraint functions on higher domains can benefit from representation. Any questions?
Well, sort of more a comment.
Yes.
I think this vector space of 2 to the n has a sort of another secret group acting on it, the spin group.
Yes.
And somehow
that has to do with the match gates.
Yeah.
That's really the match gates.
So somehow it really should be a story about these 2 different groups, not just about the...
Oh, yeah. You can think of any... In fact, the orthogonal group is very interesting as an action.
Yeah. And
different groups, definitely.
Yeah, the spin seems to be really important for the picture. And
okay. I'd like to talk to you more about that particular one. Yeah, all I'm saying is that, there are ways that you can think of these transformations in that language.
Yeah, no, I completely agree. But what I'm saying is I would suggest thinking of it in terms of a space that has 2 groups acting on it. One is this change, these kind of, the cousin of SU2, the admissible changes of basis or whatever you want to call it.
Yeah.
And then the other one is kind of coming from the problem that you want to solve. And it's the interplay between the 2 that sort of it's really beautiful.
I completely agree with you. But Jim, I also would like to suggest that there's actually more than just the match gates that's being played here. And this edge coloring, in fact, doesn't quite directly having anything to do with...
I'm not saying it should be the spin.
No,
probably
yeah.
not. But I suspect whenever you get this kind of, things that just fall into P, that there's this other group kind of hiding in the background that's
I completely agree. Yeah, absolutely. This is exactly what this is why I come to this workshop, trying to ask you guys to think about this and learn something. Okay, so now let's go back to elementary complexity theory. Okay, we have the simple function that takes 3 inputs. Each one of them takes one of those kappa colors. And the function is simply saying, I want all of them to be distinct. Okay, so this is edge coloring back. I'm at a degree 3 vertex. I want 3 triple of colors coming in. And I will say it's no good if at least 2 colors are the same. Otherwise, it's going to be okay if they're all distinct. Okay? And then you can put this into the Holant framework where you just apply the all distinct function at every vertex. Then for a 3 regular graph, this Holant value is the number of valid 3 edge coloring. Is that clear? This is just another way of saying things. Okay? The sum is going to be 1 if and only if at every vertex the all distinct constraint is satisfied. Otherwise, it's killed by the 0. But of course, you don't have to think about just this sort of function. You can think of a more general function that if x, y, z comes in k different colors, if they're all distinct, there's some value. If they're all the same, there's some value. If 2 of them are the same and one of them is different, you have some other value. Right? You can think of these. So dichotomy theorems are basically trying to classify according to every function you can put here what kind of complexity of computing this sum of product computation is all about. Okay, so in this particular case that we are going to prove, in which this edge coloring is proved, is the following function, where if they're all the same, I give you value A. If 2 are the same, 1 is different, I give you value B. And if they're all distinct, I give you C. So it's described by 3 complex numbers. Now you may wonder, why do I even go to complex? Well, it turns out that just like this transformation over here, even if the original problem was all non-negative, or 0, 1 even, the freedom that permitted by you to use these complex transformations using various eigenvalues and so on becomes very useful. So it would be useful to not restrict a priori to just 0, 1 ABCs. And of course, the all distinct one is, in this notation, is just the 0, 0, 1. Okay? So if, the only value is non-zero is 1 when they're all distinct. Otherwise, it's... Is that clear so far? I mean, everything is very elementary at this point, right? Okay, now let me just mention a little bit of the other frameworks. I've been talking about Holant problems, really. There is basically probably the best studied framework in these 3 frameworks is graph homomorphism. It came from, originally at least, came from as early as 1967. Lazilovas actually has, I think, an abiding interest in this topic, where if you look onto his website, on this particular page, there's listed something for 40 or so papers over 40 years, too, where he himself was at least the co-author of. So there's a lot of interesting and beautiful stuff was done. And the way is defined as follows. You're given an n by n symmetric, or k by k symmetric matrix. And the input is a graph. And then the output is the sum of product thing again. And now what is this sum of product? It's a sum where you assign every vertex of the input graph G to one of those kappa colors, or one of those columns or rows. And then for every particular assignment, you multiply for every edge of the input graph G of the target value where the A is. Let me illustrate this by an example. So for example, if you have the matrix of 0, 1, 1, 1, okay? And there are 2 colors, 0, 1, namely. And for every graph, this is some sort of matrix H. And then for every graph, you are assigning now vertices of the graph to be 0 or 1. Okay? You're picking the vertex or not to pick the vertex per each vertex. You're picking a subset of vertices. Okay? Subject to the constraint that for every 2 vertices that is picked 0, 0, that is no good. So you don't allow a picking of a set of vertices so that there are 2 vertices. If you think of 0 as an unpicked, 1 as picked. So little quiz, what's this problem?
Number of discrete sets.
Number of, I guess that's your terminology for vertex cover. This is vertex cover. You want to pick a set of vertices so that there are no edges hanging out there that are totally untouched. So this is a counting number vertex cover. Okay? So that's vertex cover. And if you take this matrix, then it's the number of vertex coloring. Okay, so this is saying that I allow you to assign any one of the kappa colors for every vertex, provided for every edge, it is not assigned the same on both sides. Okay? So now, for this, we have a dichotomy. This is joint work with Xi Chen and Pingyan Lu. This we worked really, really hard for. So the dichotomy theorem says that you give an arbitrary symmetric complex valued matrix. This problem, which was this partition function called a Z, okay, computing this thing, which by definition, of course, takes exponentially many. The definitional way of computing it takes exponentially many terms, but it might be that you can do it in a different way. So that's the whole point of complexity theory, right? You might do it efficiently. And the theorem says that this computation for an input G is either in polynomial time or Sharpe-Hard for the class of value.
So what's the dimension of the underlying vector space that you're operating on?
Vector space? What vector space? You mean the type, the A, all the possible A's? Or? The tractable ones, the ones that have polynomial time computability, do not form a linear subspace.
No,
Yeah, so...
No, I'm just, so if you fix, I guess, the number of, the size of the graph for vertices and edges.
You don't fix the graph, you fix the A. That sort of talks about what problem you're talking about, like vertex cover. So this 2 by 2 matrix is the A. That tells you I'm talking about vertex cover problem. Now the input is G, which has n vertices and m edges.
So it has, right, so if you have n vertices and n edges or whatever,
right.
Then
so you compute. I mean, the function is finitary computable. The question is, does it take 2 to the n steps? Or something like that.
So the naive is this 2 to the n?
Well, it's kappa to the n or something,
Kappa to the n.
Yeah.
Okay.
Yeah.
So Jin-Yi, suppose a particular matrix is hard to compute. So there's some graph for which it's hard to compute.
Right. Well, there's a sequence. I mean, there's always a complexity. It's not a single graph. So it's an infinite family of a G for which it is hard.
But it could be easy for some inputs.
Oh, yeah, of course. I mean, if I give you the empty graph, there's no nothing to...
So is it possible to tell if it's hard, if it's easy for a given graph?
Well, that's another very well-defined question, right? I mean, so what does it mean by for a given graph? For a given family of graphs, probably. You probably meant for a given family of graphs. For example, if the graph is a planar, is it possible? And this actually goes back to the match gates question, where there's a running thesis where we would say that the type of these computation of the partition function come in 3 varieties. Those which are in polynomial time, and the rest are in Sharpe-Hard, precisely. And then for those which comes in 2 precise separations, those which are over planar is easy, and those which are still hard. And the middle one is precisely those which are under holographic transformation to be solvable by match gates. So this is something we have theorems about, say, Boolean domain theorems and symmetric signatures, but not as fully general as this theorem. This theorem, I should say that, we worked very hard, but there are fantastic work before by Martin Dyer and and Greenhill, Catherine Greenhill. For the 0, 1 case, Bulatov, Grove for the non-negative case, and then Jerem, Goldberg, Grove, and Thurley for the real positive or negative case, and for the full generalities here.
So when you say planar graphs, you mean minor closed families, or just really?
Just planar, actually planar, so you can draw it on. Yes?
So do you also have the description for which A it's like that?
Yes, that's a very good question. And this actually, so this particular thing says, so let me just phrase his question properly so everyone understands what the question is. First of all, there is the question of given an A fixed, the computational problem of a given G, what's the complexity of computing the partition function of Z sub A of G? Okay, so A is fixed, A is constant. But then you can say, since there is a dichotomy, for every A, it's either this type of that part, that kind of computation that from G to Z of G. Then you can say, given A, which way is it? Okay? And this actually is doable also in polynomial time. And this is another, some work. It uses some non-trivial algebraic number theory by a thesis of Ge, who's a student of Landstrom. So this is not obvious, but it can be done. But then let me accentuate this by saying that we have actually on the face of it, a stronger theorem. Okay, this theorem says that you give me an arbitrary constraint satisfaction problem. So this can be viewed as the special case where you have a single binary symmetric function. And even in that case, it was hard. But this theorem uses a lot of work of theirs, so it's not it builds on that. Okay. And there, we don't have the decision procedure. So if you give me 17 functions, if you give me 2 functions, I don't know how to tell which way it went. But the theorem still says that the 2 functions, or 25 billion functions, is a constant, defines a CSP problem, which is the input is this, variables and the constraints apply like a graph, and then you ask the partition function, which is summing over all possible assignments of the variables and multiply over the constraints. Okay, and that partition function computation is either in P or sharp P, depending on what this set of 25 billion constant many functions are. But to tell which way it went, we don't know at this point. It is decidable if the constraint functions are non-negative. It is actually a theorem of Martin Dyer and Richarby to show that if it's 0, 1, it's decidable. Is another theorem with me and my co-authors for non-negative. But I want to emphasize there's a big difference between these kind of functions where the constraint functions are non-negative versus possibly positive and negative and complex. Because the cancellation is where the very sneaky and efficient algorithms happen, like the determinant versus permanent, if you will. Okay? If there are no cancellations, then it's relatively easy to, well, I shouldn't say that. Anyway, let me just stop here. With cancellation, it's harder because there are very unintuitive ways of doing it. So I'll show you some examples right away. So the main theorem is that the edge coloring is as a special case of this dichotomy where the 0, 0, 1 is the case, and this for every ABC is a sharp P or in polynomial. Okay? So that's the dichotomy we want to say. Until when?
Still 15 minutes.
Okay, I better go fast. Okay, so edge coloring is the 0, 0, 1 case. Okay, all right. Now let me show you some tractable problems. Okay, they're actually in polynomial time solvable, and they're not obvious. So the function is, say, for example, they're all coming in the same 5. If 2 of them are same, 1 is different, 2. If they're all different, negative 4. Boom. That problem is solvable in polynomial. Remember what the problem is? The graph comes in, you assign all exponentially many assignments, and then you evaluate this product, and you sum over all these exponentially many terms. Okay, this is polynomial time computable. And the way why it is computable is by this holographic transformation, but now over the 3x3 domain. And you express as these tensor sums, and this should really appeal to the heart of the audience here. And you express this in this orthogonal transformation of the original vectors, and this gives you a way to say that I can somehow solve it. Okay, so this is, it's not a totally obvious thing. I'm skipping a lot of details.
Confused that this seems a symmetric tensor.
Yes, it is. It is, exactly. These are symmetric ones. In general, you can say, for kappa colors and kappa square minus 6 kappa plus 4. Okay, you got the point, right? So something that are not obvious. But remember, if you want to prove dichotomy theorems, you better not prove this thing hard. It's a joke. Okay? Because it's in polynomial time. This is like a subterranean polynomial time solvable things. And you look over the sea and you really want to carve out everything, and you better not hit one of those rocks, right? I mean, you're not going to prove a polynomial time computable thing sharply hard. Or maybe that's better if you did that, but let's not go into that, right? Do you understand? So to be, sanity check, you should try to prove just those which are not in polynomial time sharply hard, and those which are actually in polynomial time, leave them alone. Don't try to prove them sharply hard. You shouldn't overreach. Does that make sense? Or maybe you want to overreach, but anyway, good. So for kappa domain 4, for example, here's something. Okay, again, minus 3 plus 4i, things that are not totally obvious. And
So, I'm a little confused. So when you show something is in P,
yeah.
are you also producing the algorithm, or
Yes.
you're just saying it?
In this case, it does. In the case of the CSP dichotomy that I mentioned that I don't have a decision procedure for, it's a little more subtle. I produce, and this is with the Shi-Chen, we produce a polynomial time algorithm. So the algorithm is actually there. It's not a purely existential proof. The algorithm is there. However, to prove that the algorithm always worked demands that a certain property of a certain infinitary object is satisfied. And this infinitary object comes from these 75 billion constraint functions. 75 billion constant, but it generates an infinitary thing, and then you either say you have the property or you don't. And if you have the property, this algorithm will always work. And if you don't have the property, then I will show otherwise it's sharply hard. So that's how the proof went there. But here it's much more constructive. We actually give the actual polynomial time algorithm for every one of those problems that we show is in polynomial time, and for everything else in this particular framework of these constraint functions of ABC, we show that it is sharply hard. We prove a reduction. Okay? So let me now move a little bit into the ideas of proof. It uses the Tutte polynomial. So this is the Tutte polynomial. And if you haven't seen this before, then not much point for me to explain. It's number of connected components and so on. Okay? And it encodes a lot of information about the graph. A special case of this, specialized into this, is the chromatic polynomial. That's the number of vertex colorings. Vertigin has a theorem that says that the Tutte polynomial is either in polynomial time or sharply hard. And it is described precisely at these points that are in polynomial time, and otherwise it's sharply hard. Okay? That's a known theorem. Now let me introduce you what is called a medial graph. So here's a graph, and you take every edge, so this is a planar graph, and you take every edge and you sort of connect an edge if the edges are incident, are next to each other to a particular region, to a particular face. Okay, so is it clear what I'm doing? So for example, this I will connect to here, connect to here, connect to here, connect back. Okay, so that's called a medial graph. And by definition, a medial graph is always 4 regular. In fact, you can define what's called a directed medial graph, where the cycles are always such that the vertices, the original vertices are inside and the original faces are the outside. So counterclockwise this way, clockwise that way. Okay. Now, a graph is Eulerian if every vertex has an even degree. Okay. And a directed graph is Eulerian if the in degree is always equal to the out degree. It's like you can go in and come out and come in and come out. You never really have to be stuck there, right? That's what. But it's not required in this definition, Eulerian, to be connected. Usually it is assumed to be connected. All right. So given a graph, a connected planar graph, there's a way to connect the Tutte polynomial evaluated at the diagonal points to a certain sum over the labelings which are called Eulerian labelings. Okay? And with various factors, and this is 2 to the number of monochromatic vertices. So let's think a little bit about what medial graph locally, direct medial graph locally, the configuration must look like. It must look like this, because this was the original edge, basically. Okay? So you come in, go out, come in, go out. Cyclically, it must be in, out, in, out. So to be Eulerian of coloring, it either is all the same color, that's fine, right? Okay, 2 in, 2 out, or 1 in, 1 out of 2 different colors. And this is one possibility, and there's another possibility, and that's the only possibility. Okay? And in that sum, it is only the monochromatic vertices that will give you a factor 2 locally, and 2 to the number of such monochromatic factors is the total sum. Otherwise, you just think this factor is 1. And in this way, you can think of the sum, the sum over the Eulerian on the directed medial graph, as a Holant problem, where the signature says it's a 2, 1, 0, 1, 0. What is 2? 2 says all 4 things are the same. That gives you 2. And this says that these 2 are the same, these 2 are the same. This says that these 2 are the same, these 2 are the same. And this is like these 2 are the same, these 2 are the same. And that's not good. That's not allowed, because the in, out, in, out. Okay? So if you think about this, it takes a little thinking, but basically this sum is the Holant problem. So the Tutte dichotomy gives me hardness over the medial graph on this particular signature, what we call signature or constraint function, 2, 1, 0, 1, 0. Okay, and now if you assign the all distinct signature in this particular graph, you can compute that it comes out to be something like this. Okay, that this is a simple way to compute. I'll just not go through it. It's, again, if they're all the same, it has to be 0 because this is distinct. So this doubly cannot equal to z, and so on and so forth. Now, if you take the gadget, which is just 2 parallel lines, then you can compute another one. Again, it's just a simple computation. And now we are ready sort of to talk about the outline of this proof of the edge coloring. We'll reduce this problem to that. Remember, this is the sum over these medial graph Eulerian partitions, which ultimately go to the Tutte polynomial that is known to be sharply hard. And we're going to reduce this to, this is the edge coloring, that for 3 regular graphs, all distinct is 3 edge coloring. And we're going to assign this thing on each one of those vertices and construct a sequence of gadgets. And again, a moment of reflection would suggest that the constraint functions on these 4 inputs can be written on as a 5-dimensional vector as an iteration of a matrix to its power over an initial F0, which is this 2 parallel lines. Okay, so this again takes a little thinking, but it's elementary. So there's I mean, at least sort of philosophically, you should agree with me that if I do this iteration, there should be a matrix iterating of things, right? So that shouldn't be a surprise. But for this particular matrix, it turns out that's the case. And then what we would like to do is to decompose it into spectral decomposition, into its eigenvalues and eigenvectors. Okay? And once I do that, then I have a very nice way of writing this into some entries where the x are the color minus 1 number to this number of iterations of 2s, where this signature is being iterated. Okay, so now this is the idea of called interpolation. I would like to somehow reduce this problem, which was, remember, this is a version of the Tutte polynomial computation. I want to reduce the computation of this to the edge coloring problem. Okay, so we assume that I have an edge coloring as a way to, as an oracle access, if you will, about this all distinct function. And assume this problem, which is the Tutte problem, where this signature appears n times. And you would replace each one of those n times by the sequence of 2s, s is another independent parameter, of this gadget, which is made up of this edge coloring signature, all distinct. And once you do that, then the polynomial as the final value can be viewed as a polynomial of this x, where the coefficients do not depend on this number s of iterations. It's encapsulated into this s. And then what you do is you evaluate this at some n+1 points, sufficiently large, polynomial many, and then you interpolate the polynomial. Once you re-interpolate the polynomial, you plug in the desired x, which gives you back the original Tutte polynomial. So this is a little fast, and if you didn't get all the details, that's okay. All I'm saying is that I have a way to transform the Tutte polynomial evaluation into the edge coloring problem, whereby I use some spectral techniques to express things as polynomials, and then when I evaluate at this potentially available problem, which is called edge coloring, at some n+1 instances, I can reconstruct a certain polynomial, which then I can reconstruct the original Tutte. So therefore, the computation of the Tutte is polynomially reducible to the edge coloring, if I could access to edge coloring, and therefore it must be hard, because originally I couldn't do it. Right? Okay, so that's the logic. Now, the few minutes of words on the an outline of the full dichotomy. It's really probably too much for me to finish. So let me skip this and give you a flavor of the structure of this proof. What I have done is told you a little bit thing here, and every little circle is sort of a theorem and lemma and what have you, some logical dependency. And yeah, it's a 70-some page thing, so a lot of work went in. But let me highlight something that has to do with the Siegel theorem, because this is how I start this talk with. Okay? So let me now define what is called a lattice condition. So give me some number of non-zero complex numbers. I ask what kind of exponents, integer exponents of xi, such that the product can equal to 1. More precisely, I want to say it satisfies the lattice condition if for any non-zero tuple of integer exponents x, subject to the sum that being 0, that this product is never equal to 1. If you take the logarithm of this, this is a linear dependency over the rationals. That's what it really is. I don't want to talk about the log because for the complex, then you have to talk about what branch you take and so on. I want to bypass that complexity. Okay, so this is the formal definition. But essentially, it is about rational dependency of these presumably transcendental numbers. Good. And now there's a theorem which I don't want to read the full thing for you, but I just want you to focus on here, that when you have these iterative matrices where the powers of which that I described to you in the 5x5 case in particular, if the eigenvalues satisfy certain lattice conditions, the one that I described, then I have a reduction. Okay, so the theorem basically says I want these eigenvalues to be sufficiently independent in the sense of the logarithm of which is rationally independent. And the actual reduction that will come out is something like this. Okay, so it's a 9x9 recurrence matrix, of which I can take out some 4 dimensions which are trivial, eigenvalues being orthogonal, so it distills down into a degree 5 polynomial, where kappa is the number of colors. And if you normalize it, you get a quintic polynomial in x with integer parameter kappa. And if you think about this kappa as another integer parameter, you have a particular polynomial with integer coefficients in 2 variables, x and y. And what we really would like to say is that for every y integer parameter, the kappa parameter, this as a quintic polynomial in x have eigenvalues of 5 eigenvalues satisfy the lattice condition. This is what we really want to do. And so presumably for every integer y bigger than or equal to 4, this is irreducible. And we can't prove that. We can prove for every fixed y, but we can't prove for every integer y bigger than or equal to 4 is irreducible. If it is irreducible, we can prove, again using Galois theory, that it satisfies the lattice condition. We do know that this polynomial have these 5 integer solutions. And of course, for these particular integer places, you don't have irreducibility. But what we would like to say is that for y bigger than or equal to 4 as an integer, it is irreducible. Okay? So now the proof sort of bifurcates into 2 parts. One deals with when it's irreducible, one deals with maybe it is not irreducible. We believe it won't be not irreducible, but we can't prove it. But nevertheless, we're going to
try to arrive at a conclusion early.
Oh, okay, so let me just finish in 2 minutes then. So what we'd like to say is that even if it's not irreducible, which we don't believe it's the case, it doesn't have linear factors. When it doesn't have linear factors, it factors into a quadratic and a cubic. And in that case, we further discuss its Galois group and trying to show that it satisfies the lattice condition. So the real crust is to say that there are no integer solutions beyond the trivial ones. And maybe I'll just, okay, let me just show one more slide. It says that the final way to show that there are no integer solutions is to appeal this device called the Puiseux series. So you expand this with these fractional Laurent expansions near the roots, and then argue that certain functions that should be integer if x and y are integer solutions would have been an integer. However, we argue that it must go down to 0, but not entirely 0. So it's going down like this with an effective constant both bounded above and below. So it would be something, a fractional number when x is large. So it would be between 0 and 1, therefore it's not integer. And that contradicts the assumption that the x and y are integer solutions to it. And this technique is sometimes called the Runge's method. So thank you very much.
So thanks for the very interesting talk. Are there any questions or comments?
Yes.
Shmuel.
Can you give just one example, let's say, of your theorem about this matrix? Let's say, what's just something that I can just understand? You know, for example, let's say if a computing permanent, you know, it's P-sharp, is it in your theorem or not?
The permanent is not technically because it's not a locally constrained problem. But there are things that are very similar to that. For example, if you take the, again, let's say take the Adama matrix of, let's say you take the matrix which is 1, 1, 1, minus 1. And that's your, graph homomorphism problem. And then you're assigning zeros or ones on every vertex and look at every edge. And the every edge, if it's 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, right? There are 4 possibilities. And only here it will contribute a negative 1. So in other words, when you take a set of vertices as thinking of taking the 1 vertices as picked, then all the edges are ignored except the edges are between 2 1s. So that's an induced subgraph. And then you're asking, is an odd or even number of induced subgraphs? Because it's a minus 1 to the power of the edges. So this question of the partition function in this particular case is the number of even induced subgraphs minus the number of odd induced subgraphs. Of course, the sum is obvious. It's 2 to the n, total number of induced subgraphs. So therefore, if you know the difference, then you know the sum. You already know the sum, so you know each parts. So this is essentially the problem of computing the number of odd induced subgraphs or the number of even induced subgraphs. It's like a permanent determinant in this case, but except the sum in this case, like permanent, is actually computable. So the determinant is also computable in this sense. So you actually get both, the even part and the odd part. So this is one of those computable problems.
So this is a computable.
That's right. That's in a polynomial time computable problem. And it's very easy to construct things that are not computable. If you put something like another root of unity over here, it will be not good.
So I guess after your theorem, I should believe that there is no way to express graph isomorphism in this class.
This is actually a theorem that these sort of globally constrained things cannot be expressed in this monadic logic and thing. But I think what you're saying is that you think graph isomorphism is neither in P nor in P complete.
I was just asking,
yeah.
How do I see directly that it can't be expressed in this class?
Yeah, it probably, that's one way to think about it, I guess, that since it's not expressible here, the dichotomy theorem doesn't apply. But I'm not so sure I actually agree with you that the graph isomorphism is not in P. So that's,
Thanks. Other question? So if not, we thank Jens.